Academic research labs face unique source of risk. Unlike industrial labs that are full of professionals, academic research lab involves inexperienced students to operate high-end instrumentation while handling dangerous biohazards. This creates an environment difficult to maintain a consistent safety culture, leading to equipment misuse and fail compliance. To address this gap, our project is guided by three objectives: to identify the hazards associated with biotechnology instruments, to conduct a HI-RARC analysis, and to establish a compliance checklist for the academic research labs to align with requirements of the Biosafety Act 2007.
Instrumentation overview. UVV spectrophotometer quantifies DNA, RNA, and bacterial cultures. Its main hazards include non-ionizing UV radiation from deuterium lamps, which damage the eyes and skin, electrical hazards during high-voltage lamp startup, and biological contamination from spilled LMO samples. These risks are controlled through engineering controls such as interlocked sample compartments and administrative measures like mandatory cool-down periods before lamp replacement. HPLC systems separate chemical and biological samples, but the high-pressure operation can cause leaks or equipment failure. They also involve toxic and flammable solvents like methanol, mechanical hazards from the auto-injector, and BSL-2 containment when handling LMO samples. Safety controls include secondary containment, solvent safety caps, chemical disinfection of LMO waste, and strict shutdown and flushing procedures. HIREC is a safety guideline established by DOSH Malaysia under the OSHA 1994. It ensures that laboratory employers provide a safe working environment for all personnel. Hazard identification involves recognizing health hazards such as biohazards, chemical exposure, and physical hazards. Safety hazards including UV radiation, broken glassware, and fire risk. Environmental hazards related to the improper disposal of LMO or hazardous chemicals. Risk assessment is conducted according to DOSH 2015 guidelines by evaluating the likelihood and severity of potential incidents based on task analysis and safety records, with risk calculated as likelihood multiplied by severity. Risk control then follows the hierarchy of control, beginning with elimination or substitution, followed by engineering controls, administrative measures such as SOPs, and personal protective equipment like safety goggles and nitrile glove.
In academic research, safety and instrumentation management are the foundation of every successful experiment. We begin with addressing core hazards. Laboratory environment face constant risk from chemical agents such as flammable and corrosive reagent, as well as physical hazards like electrical shock or high-pressure gas explosion from complex instrumentation. To manage this, we employ HARAC, which stands for Hazard Identification, Risk Assessment, Risk Control. This allows us to classify activities and assess risk systematically. We follow the hierarchy of control, prioritizing air engineering solutions like local exhaust ventilation to manage contaminant at the source before relying on individual practices. Central to our protocol are the 4 biosafety levels. These range from BSL-1 for well-characterized, non-pathogenic agent up to BSL-4 for life-threatening, exotic pathogen. Each level dictates specific requirements for training and equipment maintenance. Moving to the regulatory landscape, the Biosafety Act 2007 aligns Malaysia with the Cartagena Protocol. It specifically regulates the use of living modified organisms to ensure biotechnology doesn't compromise ecological or human safety. This works alongside OSHA 1994, which mandates risk assessment and OSH coordinators. Finally, MS ISO EC 17025 provide the framework for validating our data and maintaining lab credibility. By integrating this protocol and laws, we create a robust safety culture that protects both the researcher and the integrity of the science.
The Biosafety Act 2007 provides the legal framework regulating living modified organisms, biotechnology, and hazardous biological materials in Malaysia, ensuring the controlled development and use of genetic products. Facilities handling biological agents must comply with these requirements to minimize risks. Instruments such as biosafety cabinets must operate under contamination control measures, and biological equipment must be regularly validated and maintained in accordance with ISO 17K25 and biosafety standards. For genetically modified organisms, laboratory must follow appropriate biosafety containment levels based on risk assessment and maintain proper records. Biological waste must be segregated, inactivated by autoclaving or chemical disinfection, and disposed of according to approved procedures. SOPs. First, ensure the laboratory workspace is clean, disinfected, and free from spills before starting any operation to maintain safety and data integrity. For UV spectrophotometer, clean and disinfect the workspace before use. Warm up the instrument to stabilize the light source, then calibrate it by blanking with solvent or ultra-pure water. During measurement, wear appropriate personal protective equipment and keep the sample compartment closed. For HPLC operation, perform pre-start checks on tubing connections and solvent reservoirs. Push the system to remove air bubbles before analysis and verify system suitability prior to sample injection. Finally, for biological waste management, dispose of sharp in puncture-proof containers without recapping. All waste must be properly labeled, documented, and tracked to ensure regulatory compliance.
The first challenge in implementing biosafety and laboratory safety compliance is resource limitation and budget constraint. To achieve compliance, significant financial investment is required for regular professional calibration and the purchase of expensive certified reference material. Additionally, laboratory renovation are often needed to accommodate specific containment infrastructure. Furthermore, the knowledge, attitude, and practice gaps such as lack of awareness and understanding of regulatory requirements can further limit the effective implementation of safety measures. The heavy documentation requirement for this regulation also frequently burdens staff and students. For instance, OSHA 1994 requires that lab maintain updated chemical register, which often leads to a culture where people focus more on finishing paperwork rather than actually making the lab a safer place. Lastly, the functional state of safety equipment is a specific local challenge highlighted in recent research. If regular maintenance is neglected, issues like low water pressure in emergency shower can occur. To address the challenges that I mentioned just now, strategy improvement can be implemented. These include the use of hands-on demonstration of laboratory activity, which helps students to understand the relevance of safety procedure to their own work. Next, the documentation burden can be reduced by integrating QR code. This code can be placed on equipment and chemical storage area, allowing students to access standard operating procedure and safety data sheet instantly via mobile devices. Moreover, regular audits should be conducted by a biosafety officer to help identify gaps early and promote consistent enforcement across departments. Finally, real-time indoor air quality monitoring can be integrated with chemical health risk assessment to provide a more comprehensive data-driven approach to manage exposure risk.
Based on our findings, we recommend 4 strategies to address the safety gap in academic research labs. First, mandatory hands-on certification to ensure students' competence in proper instrument handling. Second, SOPs are digitalized with QR codes, giving instant access to protocols. Third, assurance requires routine audits to verify ongoing legal compliance. Finally, safety infrastructure and preventive maintenance must be prioritized for safety. In conclusion, our study confirms that academic research labs face challenges of high student turnover and high-risk assets. The HIRARC analysis proves that these risks are manageable. By applying strict controls, we can significantly reduce incident rates. Ultimately, lab safety and instrumentation management is a legal requirement. By following our checklist to align with the Biosafety Act 2007, OSHA 1994, and the ISO, we ensure our lab remains a safe and compliant research facility. Thank you.